In the previous video, we have calculated fundamental group of finite wedge of circles. Now we will generalize this result to infinite number of circles having a point in common. So firstly we define coherent with the subspaces. So let us take X to be a space which is union of the subspaces X alpha where this alpha belongs to the index set J. The topology of this space X that is said to be coherent with the subspaces X alphas if and only if a subset C in X, this is closed in X whenever C intersection X alpha, this is closed in X alpha for each alpha. Or equivalently, we can say C is open in X whenever C intersection X alpha is open in X alpha for each alpha. Now, previously we have taken X to be the union of finitely many subspaces X1, X2, Xn, and we have taken there the condition of Hausdorffness of space X. But we are taking here coherent topology. If X is finitely if X is union of finitely many subspaces X1, X2, Xn, then the topology is automatically coherent with the subspaces, because if C intersection Xi, that is closed in Xi for each I varying from 1 to n, then C is just union of all these sets, and that will be a finite union, so it will be always closed in X. So whenever X is union of finitely many subspaces, then it is automatically coherent. So now we define wedge of circles S alphas. Now suppose X is a space which is union of S alphas for alpha belong to J, and each of S alpha, this is homeomorphic to the circle S1. Now assume there is a point P in X such that S alpha intersection S beta, that is just the point P. Means all these S alphas, they have just P point as their common points. So whenever alpha is not equal to beta, their intersection is the point P. Now we assume here if topology of X is coherent with all these subspaces S alphas, then X is called wedge of circles S alphas. Now in the finite case, we have involved the Hausdorff condition instead of coherent conditions for defining wedge of circles. But here we have involved coherent conditions. Now we know that Hausdorff condition, that uh, if we assume the Hausdorff condition, then the coherence condition that always followed. And in the infinite case, if we include the coherent condition as a part of the definition of wedge of circles, then it will include the Hausdorff condition as well. So now we prove firstly a lemma, and later on in the theorem we will calculate the fundamental group of this wedge of circles. So now if X is wedge of circles S alphas, then X is normal. Firstly, we want to prove wedge of circles S alphas, that is a normal space. And secondly, we want to prove any compact subspace of X is contained in finitely many circles S alphas. If we take any compact subset of X, that will be contained in only union of finitely many circles S alphas. So let us prove firstly X is normal. Now we know that in this case, in wedge of circles, one-point sets are closed. So to prove normality, we take two disjoint closed sets and we will prove there exist disjoint open sets containing them. So A and B, suppose these are disjoint closed sets in X. And because we are taking them to be disjoint sets, so at the most one of these two sets contain the point P. So we assume that B does not contain point P. Here this P is the common point of all the circles S alphas, because we are assuming X is wedge of circles S alphas. So now we take these two sets, the point P union the set A intersection S alpha, and the other set is B intersection S alpha. Now if A and B are closed in X, because we are assuming that the topology of X is coherent with the subspaces S alpha, so A intersection S alpha and B intersection S alpha, these are closed sets in S alpha. So this set P union A intersection S alpha, this is always closed in S alpha, because this is finite union of two closed sets. So now we have these two are closed sets in set S alpha, and S alpha is homeomorphic to circle S1, so that is normal. So there exist disjoint open sets U alpha and V alpha in S alpha, such that one of these sets is contained in U alpha and other is contained in V alpha. So now we can see these are closed sets in S alpha. Therefore, there exist disjoint open sets U alpha and V alpha in S alpha, such that the set P union A intersection S alpha, this is contained in U alpha, and the other set is contained in V alpha. Now let us take U to be union of U alphas and V to be union of V alphas. Then this U and V are also disjoint, because all U alpha V alphas are disjoint. So they are disjoint. And now U intersection S alpha, that will be U alpha, because all the sets U alpha, they contain point P. And similarly, V intersection S alpha, that is V alpha, because no set V alpha contains point P. So now this U and V, because U intersection S alpha, this is U alpha, which is open in S alpha. Similarly, V intersection S alpha, this is V alpha, which is open in S alpha. So basically, U and V, they are open in X. And A is contained in U and B is contained in V. because B intersection S alpha is contained in B alpha. So taking their union over alphas, so union of B intersection union S alpha, so that will be contained in union B alpha, which means B is contained in B. Similarly, A is contained in U. So this proves that X is normal. Now we prove the second part of the lemma. The second part says if we have a compact subspace, then that is contained in only finite number of circles, S alphas. So let's see, be a compact subspace of X. Now for each alpha, we choose a point X alpha in C intersection S alpha minus P. Now here we will prove that these points X alphas, they are just a finite number of points. Means we will prove that C intersection S alpha minus P, this is empty set except for a finite number of sets. So if C intersection S alpha minus P will be empty for except for a finite number of sets, then it will be proved that C is contained in only a finite number of circles S alphas. So we will prove that this collection of points X alphas, that is just a finite collection. So we take D to be collection of all these X alphas. Now this is a closed set because if we take intersection of D with each S alpha, then that is either singleton set or it is empty. And both the sets are closed. So if D intersection S alpha is closed in S alpha, then D is closed in X because of the coherence condition. Now for the same reason, D is also closed in X because if we each subset of D. Here we have proved D is closed set in X. So similarly, we can prove each subset of D is closed in X. Because if we take any subset of D and we take intersection with S alpha, then that is also either singleton or empty set. So every subset of D is closed. So if every subset of D is closed, it means D has a discrete topology. Or we can say D is a discrete subspace. So it is a closed discrete subspace of X. And this is contained in C because D is collection of all the points X alphas and we have chosen points X alphas to be in C. So this is contained in C. Now we are assuming that C is a compact subspace and we have proved that C contains a closed discrete subspace. But that is only possible if D is finite. Since C is compact, therefore D is finite. It means we can choose point X alpha only in finite number of spaces C intersection S alpha minus P. Otherwise it will be empty. So it means C is contained in only a finite number of circles S alphas. So now we prove the theorem in which we will find out the fundamental group of wedge of circles. So now here we assume that X is wedge of circles S alphas and P is the common point of all these S alphas whenever alpha is not equal to beta. Then we want to prove that the fundamental group of X with respect to P, this is a free group. And if F alpha is a loop in S alpha, which represents a generator of fundamental group of S alpha with respect to P, then the loops F alpha, they represent a system of free generators. For the fundamental group of X with respect to P. So let us prove. Now we know there is a inclusion mapping from S alpha to P, and let us take I alpha to be the homomorphism induced by inclusion map pi1 SP to pi1 XP. So let this I alpha be homomorphism induced by inclusion. And let us take G alpha is image of I alpha. Now if F is any loop in X based at P, because the loop is continuous map from I to X, so its image set is also compact because the closed interval 0, 1 is compact. So image set of F is compact. And from the previous lemma, if a subset is compact in X, then it is contained in union of finite number of spaces S alpha. So it means F lies in some finite union of subspaces S alphas. Now if we take two loops F and G, which are path homotopic in space X, then because each of them lies in some finite union of subspaces S alpha, then they are actually path homotopic in some finite union of subspaces S alpha. So it means the groups G alpha, they generate pi1 xp because G alpha is image of I alpha. And we are saying that any path homotopy class that is basically element of pi1 S alpha P for some finite number of spaces S alphas. So it means the groups G alpha, they will generate pi1 xp. Because let us take F be a loop in X, then we have proved that F lies in finite union of subspaces. So suppose F lies in S alpha 1 union S alpha 2 up to union S alpha n. Suppose these are the finite number of indices. Then we have proved the case for the finite number of circles having a point in common. So it means this element, this is basically product of elements of, this is product of elements of the groups G alpha 1, G alpha 2 up to G alpha n. That means every element of pi1 xp, that is just finite product of elements of G alpha 1, G alpha 2 up to G alpha n. So that means we can say that all these groups G alphas, they generate pi 1 xp. Now these I betas, they are monomorphisms. Second thing, this I beta, this is monomorphism for every beta. Because to prove monomorphism, we will prove that we will prove that the kernel of this I beta, that is identity. Means if we have an element whose image is 0, then that element itself will be 0. So here we will assume that f is a loop in S beta, which is path homotopic to constant in X. Because if this is identity element, if f is the representative of that element whose image is identity under this I beta mapping. Now we know if f is a loop in S beta, then its image under I beta, that will be a homotopic class of f in space X. So that will be identity, which means f is path homotopic to constant. In X. Now if f is path homotopic to constant path in X, that means this homotopy is actually infinite number of subspaces S alphas. So f is path homotopic to constant in some finite union of spaces S alphas. So again we can apply the finite case. It means f is path homotopic to constant in S beta. So if f is path homotopic, but f is a loop actually in S beta, so it means f is path homotopic to constant in, so f is path homotopic to constant in space S beta itself. So it proves that the homotopy class of f is actually identity element, which means this is a I beta is a monomorphism. So it means the groups G alpha, they generate pi 1 xp. So now we will prove that this is actually free group pi 1 xp, which means we have to prove that every element which can be written as a product of elements of the groups G alpha 1, G alpha n, that is in just a unique manner. So for that, we will assume that there exists a reduced non-empty word, because we know identity element is represented by a reduced empty word. But let us say this is reduced non-empty word W, which is G alpha 1, G alpha 2 up to G alpha n, where all these G alphas, they are elements of the groups capital G alphas. So let us say this is a non-empty word which represents the identity element. Means basically we are assuming that except the empty word, there is another non-empty word which represents the identity element of the group pi 1 xp. Now suppose f is a path, closed path in space X, because it represents the identity element of pi 1 xp. So suppose f is a loop in X whose path homotopy class is represented by W, which means path homotopy class of f, that is just product of all these. So we can say this is given by G alpha 1 up to G alpha n. Now because f is path homotopic to constant because this basically G alpha 1, G alpha n, this is the word which represents the identity element. It means F is homotopic to the identity, F is homotopic to constant path in X. But if F is homotopic to constant path in X, then it is homotopic to constant in some finite union of S alphas. And that is a contradiction to the previous theorem, because in finite case we have proved that if we have X, which is wedge of finite number of circles, then pi 1 xp, that is a free group. That means every element has a unique representation as a product of elements of the groups pi 1 S alpha p. But here we are proving that this F is homotopic to a constant, and here this constant is represented by this non-empty word, which means the constant has two different identity element that has two different representations. One is by empty word and other is by non-empty word. So it is a contradiction to the finite case. So it means this in this case also pi 1 xp, that is a free group. And obviously these f1, f2, f alpha, these are free system of generators. If S alpha, that is a loop in S alpha representing a generator of pi 1 S alpha p. So this completes the proof of the theorem.